All right, now what we're talking about here is not that you have been deliberately misled, but you have been allowed to believe that all these chemical reactions take place and they go like, we're going to use this little A as the coefficient of this reactant A, this little B is the coefficient of the reactant B. And what we've talked about almost exclusively is the fact that until we run out of the limiting reactant, we produce product, right? And if we don't run out of the limiting reactant, we produce product forever, right? Well, in many, many cases, that's not true. In many cases, what happens is the product concentration starts to build, and we start to create this reverse pressure on the amount of products. The concentration of the products goes up, and we get to the point where the reaction starts to reverse. The concentration of the product gets so high that every time the reactants come together and produce another product, boom, the products dissociate and go back to reactant, right? And that's what we call equilibrium. That's what we call a dynamic equilibrium. And so if you check the concentration of the reactants or the products, you know, day after day after day, hour after hour, whatever, you would see no change in concentration, and you would say, oh my gosh, this thing has stopped. But it hasn't stopped at all, okay? Make sure you understand it's a dynamic equilibrium. What it means is that the reaction is going forward at the exact rate as it is going backwards, okay? And we go way back to stuff we talked about a long time ago. And, you know, one of the major things that affects a reaction going forward and the rate of reaction is the concentration, right? As well as the temperature, but the concentration is what we're looking at in this particular context, okay? So this is what we call a dynamic equilibrium, and you look at this on page, you know, if you look at your book, it's you look at it's Le Chatelier, write that down, E-L-I-E-R, Le Chatelier's principle, okay? And what that says basically is that if you have a situation that comes to an equilibrium, a dynamic equilibrium, and you stress that system, you know, a system, we're talking about a closed loop. We're looking at the equation by itself, okay? And we stress the situation comes to equilibrium, and we put it under stress by adding reactant or by adding product or increasing the temperature or decreasing the temperature or whatever. The reaction or the equilibrium will shift in such a way as to reduce the stress. It doesn't mean the equilibrium will stay exactly the same, but it will shift to reduce the stress. In other words, if you add reactant to this equilibrium, it will shift and produce more product, okay? And you know, the point at which this reaction goes forward the fastest is at time zero, right? When there is no product been produced yet. We put the two reactants together and boom, the reaction starts to go forward as fast as it's going to go, okay? And then what happens from that moment on, the concentration of reactants is being decreased, right? Because they're being used up to produce products, and the concentration of products is being increased, right? And so you finally reach this point where you reach this equilibrium, okay? And that's what we're talking about. A thing on your state test, your SOL test, is they're going to ask you probably, if this is an endothermic reaction, where would we see the energy on this if we used it as a product or reactant? It would be on the reactant side, that's right. And the other way to show that would be a positive change in energy, right? Would be endothermic. Well, if you have an endothermic reaction, in other words, if energy shows up over here on the reactant side and you increase the temperature of the whole system, it's just like adding more reactant. So it's going to force it towards product, right? If it's an exothermic reaction, and you increase the temperature on the system, it's just like adding a product, and it's going to tend to shift it back towards reactant. Got it? And that's kind of a review, but that's Le Chatelier's principle, and that's chapter 18. That's page, there's a nice little brief description on it right there on page 598, okay? Or you can Google it and probably get even better descriptions, you know, verbal descriptions, but that's Le Chatelier's principle, okay? But anyway, what we're doing here is we're getting ready to talk about the same situation here with acids and bases, and I want to show you real quick that, you know, we have a consistent idea all the way through all these concepts, okay? And so what we look at in this equilibrium, we say, well, how far does it go, right? And so Mr. Gonzalez says, well, it goes pretty far. And Mr. Cotton says, well, I don't think it goes that far. And Miss Fuel says, well, it goes. I mean, it goes pretty far in my mind, you know. But so those are qualitative statements, right? So we want to quantify it. In chemistry, how do you quantify it? Well, first of all, you call it the equilibrium constant, KEQ, okay? And this is a long-winded description of what it is precisely, but you need to know it, okay? You need to know it, and I feel obligated to expose you to it, okay? So what it is, and the way you say it is the mathematical product, right? You multiply the molar concentrations of the products, and each of those molar concentrations is raised to a power equal to the coefficient in the balanced chemical equation. So the way it looks is, and this bracket means moles per liter, okay? So it's the molar concentration of C raised to this power multiplied by the molar concentration of the other product in this example raised to this power, and then that's divided by the mathematical product of the molar concentration of the reactants. And they're also raised to the power that you see in the balanced chemical equation. Now, you know, of course, a lot of times this coefficient is 1, so there's not going to be an exponent. But if it is 2 or 3 or whatever that is, it's not a coefficient anymore. It becomes an exponent, okay? But the thing I want you to look at here and understand how straightforward this really is this is comparing the quantity of products to the quantity of reactants, right? Now look at this just from a logical point of view. What this thing says is that these reactants are going to go forward and produce these products, right? Well, the more products you produce, the bigger this number in the numerator. Also, the smaller the number in the numerator, right? So the larger this KEQ value, right? Makes sense, doesn't it? And if it only goes a very short distance here, then this number in the numerator is going to be very small, and this number is going to be large, relatively large compared to the product number, right? So the smaller the KEQ. You got it? So the KEQ gives you a measurable quantity of how far the reaction goes forward. Yes? Hello? Well, when we shift over to the idea about acids, remember, in the simplest form, we say an acid would be a hydrogen ion bonded to an anion. And since acids are electrolytes, right? And, you know, they could be weak or strong or pretty weak or pretty strong, right? So there's a you know, a degree of ionization of this acid, and it would ionize in this simplest form into hydrogen ions and this anion, right? Well, if we looked at this in terms of this, then we would talk about how strong this acid is by saying that it would be the molar concentration of the hydrogen ion multiplied by the molar concentration of the anion. And of course, if there is an exponent, it would be there, divided by the molar concentration of the acid that did not dissociate, right? Got it? And that's called the ionization constant. You know, that's the ionization constant for the water, okay? But we abbreviate it for acids in particular and call it Ka, okay? And that's the ionization of the acid, right? And if it's a base, what do you think we call it? Kb. It's the ionization of the base. Okay? The ionization of the base. Okay? Now, water itself ionizes. How many of you knew that? That in pure water, the purest water you could possibly conceive of, you distilled it or however else you wanted to purify it, right? That there's a small quantity of that water that would dissociate into hydrogen ions and hydroxide ions. right? And how would you express the degree of ionization of that water? Same way, right? Same way. Now, you start to see how many related questions you could have on that SOL, right? That state test that relate to understanding that this is a relationship between the products and the reactants. How many of you remember how we determined whether a reaction was endothermic or exothermic using the enthalpy values for the reactants and the products? It was products minus. It was the sum of the enthalpy changes for the enthalpy values for the products minus reactants, right? Well, here it's products divided by reactants, okay? Right? Division is like the big sister of subtraction. Yes? So there's about three or four potential questions right there on that page right in front of you, okay, that you need to try to get a grip on. Now, I'm going to post this recording. I suggest you look at it at least one more time before that test, okay? But let's go back to this ionization issue on water, okay? So if we look at the KW here, it's going to equal what? The molar concentration of the hydrogen ion multiplied by the molar concentration of the hydroxide ion divided by what? The molar concentration of the water that did not dissociate, right? Piece of cake, right? Well, it has been determined by measuring pH and so on and so forth, and I think they do that with like electrical conductance and resistance and whatnot, because remember, they're electrolytes, right? It has been determined that this value right here equals 1 times 10 to the negative 14. Okay? Now, if that's true, and knowing that one hydrogen, every time you produce a hydrogen ion, there's also a hydroxide ion produced, then these two numbers must be equal, yes? And so then they would equal 1 times 10 to the negative 7, 1 times 10 to the negative 7, right? Equals 1 times 10 to the negative 14. Now, this value right here is what? It's 0.00000001, right? In other words, that's how many, 1/10,000,000th, right? That's how many dissociate. Got it? So if we just use this value of 1, and we took this baby out here this far, then how many do not? 1, 2, 3, 4, 5, right? So we'd put that value would be here, right? Well, Mr. Allen, I'm not sure where you come from, but where I come from, we call that 1, right? And it's not that we don't know that it's not exactly 1. It's that for practical purposes, there's no point in using any other value, right? So the KEQ, or the ionization constant for water, which we call KW, equals 1 times 10 to the negative 7 multiplied by 1 times 10 to the negative 7, which equals 1 times 10 to the negative 14. And it's over 1, so we don't write the 1, right? Okay? So that is KW. And that is also the key to understanding acid base. Okay? Everybody got this down that wants it? Hello? Now, yeah? Now, I'm going to give you a sheet here. We'll call this page 2. And I'm going to call it the Bible, the acid-base Bible, okay? These calculations and these relationships are all you'll need to do to answer all these questions concerning, the problems concerning acid-base, okay? So we said, let me restate this, we said that the kW equals 1 times 10 to the negative 7 times 1 times 10 to the negative 7, which equals 1 times 10 to the negative 14. Everybody got that? Yes? So to restate that, we're saying that the kW then, now this is for water, right? And an acid, we said, was a substance that increased the hydrogen ion concentration in aqueous solution, right, Ms. Reynoso? So if it's increasing the hydrogen ion concentration, it's understood it's decreasing the hydroxide ion concentration, right? So now here we can think of this as pure water. So now we can think of this as the kW of water, of an aqueous solution that has a pH other than 7, right? So we restate it and we say it equals the hydrogen ion concentration, and that's brackets is moles per liter, multiplied by the hydroxide ion concentration, right? And whatever those two concentrations are, the mathematical product will equal 1 times 10 to the negative 14. Got it? Okay? Now, if you had looked ahead and looked at the problems, the practice problems on page, I think it's 502, you would see that they're giving you one of these values here and asking you for the other. Well, it makes it very easy if you look at this and you say, well, if that's the case, then the hydrogen ion concentration is going to equal what? 1 times 10 to the negative 14 divided by hydroxide ion concentration. That's one set of problems, right? If it gives you the hydrogen ion concentration, says what's the hydroxide ion concentration, then it becomes 1 times 10 to the negative 14 divided by the hydrogen ion concentration, right? And these are the practice problems on page 502, I believe. Page 502, okay? So I'm going to call this item 1, and so we'll call this 1A and 1B, okay? This is the fact. This is the way you'd use it. Got me? Yes? Hello? So, if we look at the pH scale, and we say, well, the pH scale is telling us, is giving us a way to quantify the number of hydrogen ions in any aqueous solution, right, Mr. Cotton? Then where does the pH scale come from? The pH scale comes directly from the kW, okay? And what we do is we take the negative log on your calculator, it's just like it says, negative log of the kW is going to equal the pH. Now, the log of this number would be negative 7, right? The negative log would be 7. So what do you do with numbers when you multiply numbers that have exponents and you multiply the exponents? You add them. So another way to restate this right here, statement number 1, is to say that the pH plus the POH always equals what? 14. Right? The pH plus the POH always equals 14. Okay? And an example would be, let's write this down as an example, and we'll say 100% water. The pH, the negative log of the hydrogen ion concentration would be 7. The negative log of the hydroxide ion concentration would be 7. 7 plus 7 equals 14. If the pH, if the hydrogen ion concentration goes up, then what happens to the negative log? Goes down, right? Which is smaller, Miss Fuel, 10 to the negative 7 or 10 to the negative 3? 10 to the negative 7 is the smaller number, right? 10 to the negative 3 is a larger number. That's why when the pH goes down, it's actually telling you the hydrogen ion concentration is going up, right? Got it? And you have to think about that. It's not difficult. You got to think about that. But anyway, that's idea number 2 there, okay? And the consequences of number 2 are this, that if you're looking for the hydrogen ion, if you're looking for the pH, and you have the POH, the pH is going to equal 14 minus the POH. And, of course, if you're looking for the POH, and you have the pH, the POH is going to equal 14 minus the pH. Right? Everybody with me? So you see what we're doing here, what we're saying here, Ms. Grimstead, is this. That when we talk about the Kw, knowing that the hydrogen ion concentration multiplied by the hydroxide ion concentration equals 1 times 10 to the negative 14, we're really saying the same thing when we say the pH plus the POH equals 14, because now we know the pH is the negative log of the hydrogen ion concentration, right? And that's a mouthful, but it's really not a very difficult thing to grasp, right? And particularly with your calculators, it's just a couple finger pokes from converting between one and the other, right? Okay. Now the third thing that we have to have, and you would come to this, you would ask this question here shortly anyway. What if you're given the pH and you need to know the hydrogen ion concentration? It's fairly straightforward, okay? The antilog on your calculator, that's the second key, second log, okay, of the negative pH equals the hydrogen ion concentration, right? And we're going to practice these in a minute. And also the antilog, or the second log, of the negative POH equals hydroxide ion concentration. And so you take that information up in to answer any one of these 1A, 1B, 2A, 2B type questions, right? So you can move back and forth between any one of them. What you want to look at is here. If you're given one of these 4, hydrogen ion concentration, hydroxide ion concentration, pH, or POH, you can convert to any of the other 3. Yes? See that? And we're going to practice that here in just a second. Okay? So these questions right here, somebody help me and figure out what page these are on. These questions right here are on page 502, I believe. And then over here, these practice problems right here are on page 505. Huh? 505 and 6. And then these questions right here are practice problems that you find on page 508, right? And then, of course, you got the section review questions on 509, right? Okay? So what I'm telling you and what we're going to work on here in a second is I want you to have this written down, Ms. Fuel, and I want you to work on those practice problems and section review questions, and I want you to have confidence that the key to answering those questions is right there on that paper, right? And then you try to figure out how you're going to answer them from that information on that paper, okay? There's a couple things I want you to remember here, okay? A couple little things I want you to remember, because it's going to ask you, you know, it may use molarity and hydrogen ion concentration, so on and so forth interchangeably. Well, the concentration is always in moles per liter, right? Okay. And this bracket right here means what, Miss Briggs? That is the molarity. Okay. And what is molarity? That's moles of solute. Okay. In these particular problems right here, we're talking hydrogen ions or hydroxide ions, right? Moles of solute per liter of solution. Okay? right? And the next thing we want to know is that, and this is particularly important for titrations and neutralizations, at pH 7, let's say at pH 7, the hydrogen ion concentration equals the hydroxide ion concentration. Okay? And that's, you want to know this for titration problems and or neutralization, okay? And so what happens here in a titration is you take a known molarity of acid or base, you know exactly the molarity and you know the volume, and you neutralize a known volume of either the acid or the base, the opposite, right? And so once you know exactly the volume, right, of the molarity solution you use, you can calculate the number of hydrogen ions or hydroxide ions, whichever your standard was, right? And you know that's equal to the other ion in the unknown. So you can calculate the molarity or the pH of the other solution. That's how we do this. And this is section 2 of chapter 15. Okay? That's how you solve those problems. And the other thing you want to remember is that always keep in mind about these dissociations. So if sodium hydroxide, for instance, dissociates into one sodium ion and one hydroxide ion, nobody has much trouble with that. But it's easy, Mr. Scalzo, for people to forget that if you're looking at an ion, a cation, that has more than a +1 charge, it's going to carry more than one hydroxide, right? So you have to look at this, and you're going to get a calcium here just like you did one calcium there, just like you had one sodium. But here, you're going to have 2 hydroxides, right? You got me? So the molarity or the hydroxide ion concentration will be twice the molarity of the calcium hydroxide, right? Because it's a strong base. Yes? Now, what we want to do here is we want to work these problems starting with 502, and then you can move right along, right on, and ask questions. And I want you to be confident that the key to answering all those questions is right there on that page. Okay?